Hello everyone. In this video I will walk you through my end-to-end MLOps project on the MNIST digit classification problem. So we'll go step by step from the data processing to model training to MLflow tracking, the drift detection, automated retraining, and the final deployment with the FastAPI and the Docker. So by the end you will see how the full machine learning lifecycle is managed in a production ready way. That's the aim of this project. So to start with the dataset, so we start with the MNIST dataset, which is a very simple dataset of handwritten digits containing 28 cross 28 grayscale images, and each image is normalized to values of between 0 to 1 during the pre-processing step. And for this I have used the PyTorch data loaders along with Spark. And for large scale simulation we usually use Parquet files, which is integrated in the DVC pipeline, wherein the existing dataset is converted to Parquet annotations with distributed Spark, so that the training can be scaled. That's the aim of this project, to scale the training to a larger dataset. So here I will be using the Spark as a tool to do the pre-processing in a distributed way. So that's one thing, and I've also set up some CI/CD pipelines for PyTests for running some integration tests for the data loading, the training pipeline, and so as we push the entire code base to the GitHub, the entire CI/CD pipeline runs. So that's one part of the project, and yeah. So this shows the basic diagram of the project of a very high level architecture, wherein we have the DVC versioning set up in the initial stage where the raw images are pre-processed, and then the Parquet files are generated in a distributed way, followed by a model training stage where we'll be using these generated Parquet annotations and the images to train our different models, and then we'll compare their results, and all the model logs including the artifacts, the evaluation files, the inferences are stored in MLflow to track the artifacts and produce reproducible trainings in future. And the entire endpoint is managed by the FastAPI, wherein I will be giving an endpoint for predict, wherein we'll be giving in one image as an input, and we'll get to see the classification of that image. And this entire setup is Dockerized, so that means it can run across different systems, and the API service, the training and everything has been Dockerized here. Followed by which I also included a method for drift detection, wherein if the input distribution changes, then that should trigger an alert, followed by which a task of auto retraining can be triggered as well. So that's a very high level overview of the project. So moving forward, the entire code repository is hosted in my open source repository, which can be found here, and I have also included some of the steps and the way to run this project from start to beginning, so that can be used including all the commands for FastAPI, containerization, CI/CD, as well as the repository structure and some of the references for making this project. So yeah, moving to the next part, basically I will be showing you how I have made this pipeline to train the algorithm. So for this purpose I have trained two sets of algorithms. So one is the CNN model, which is a plain CNN model, and the next one is CNN+SVM, a transfer learning model. So let's start with that. So the baseline model is a simple convolution network. It learns to classify images into 10 classes from digits 0 to 9. And the loss that has been used here is cross entropy loss for multi-class classification. And the second model which I've used here is the CNN+SVM, which basically takes the features generated by the CNN layers and feeds it to the SVM support vector machine, and then does the classification of 10 classes. So here I will compare the results and everything in the MLflow tracking URI, so that we can see how the training has progressed and what are the results coming out of it. So as I said, MLflow will be used as a central experiment tracking tool for this entire project. During each run, the MLflow will log parameters like the learning rate, batch size, Spark configs, and it also logs the metrics like accuracy, training time, and feature extraction time. As you will see in the second model, where there's a feature extraction involved from the CNN layer. So all the artifacts, including the plots, reports, reference, drift statistics, and are already stored automatically there. And the best model pipeline, which is the CNN feature extractor in my case, is also registered in the MLflow registry and promoted to the production stage. So let's start with the first step, wherein so here I have already set up the data. The data DVC is set up. The data is processed into Parquet files. Here you can see the test Parquet and the train Parquet, and these are the raw data set which is downloaded from the source of MNIST. So this is the pre-processing step, wherein after which we get Parquet files available for training. And the next step is we will use this pre-processed files to perform training. So here we have our file called Python source train, which will, so for now I will be showing you the demo for training on only a set of 200 samples for just a pipeline overview, but the results we can already see in the report, which has a complete model trained version of it. Okay, so let's start with that. So I've activated the virtual environment which I've used for this project. So if I just launch this script, it should automatically start the training process on 200 dataset. Yeah, as you can see, it's a dry run containing 200 samples, test 100 samples. It will run for 5 epochs, the CNN training, and we can already see the CNN accuracy has given us 57%. So that's with the first model. Now the second model training is in progress, wherein I will extract the features from this trained CNN model and feed it to the support vector machine for performing multi-class classification. So that's the next step which is happening right now. Yeah, so as we can already see, the CNN plus the SVM accuracy is far better than the CNN only model. So that states that our CNN plus SVM ensemble is working much better. So right now what it is doing is it is pushing the model to the production. So we have seen it has created a version 4 of the model, of the MNIST best model, and yeah. So right now the entire code, artifact, the metrics, the model has been pushed to the MLflow registry. Now we will just launch the MLflow URI to check. Okay, let's enable the environment. So now once we launch this MLflow URI, we can see our model in the MLflow tracking dashboard, which is available here. So this is the experiment which I just launched, and we can see the logs are already come up with 2 minutes ago, 1 minute ago. So here there are 3 runs basically. The first run is that of the only CNN model. This is the only CNN plus SVM model, and this run is basically for pushing the model to the production. So if you just see the CNN augmented runs here, we can see the parameters logged here: dry run, batch size, epochs, the learning rate, and the model type, as well as the metrics like how much time it took, the accuracy. As we saw before, the accuracy for CNN was around 57%. The validation loss, the training loss, and the validation accuracy. followed by which we can also see some of the model metrics as graphs here. This shows the training time, this shows the accuracy, this shows the training accuracy over 5 epochs which we just saw. This is the validation loss, the training loss, the validation accuracy. So this is expected. The validation and training loss should go down as the epoch progresses, whereas the validation accuracy and training accuracy should improve as the epoch progresses. And there are certain artifacts which are logged, like the plots. For example, we can see the confusion matrix here plotted, the CNN learning curves here, the CNN sample predictions as well. So here T stands for the target, P stands for predicted. So target is 7, predicted is 7. So as this is just a dummy model train, so we can see the performance for it confuses in some of the tough classification, but more or less this is just as inference. We also have a class-wise classification report as well for this. So this basically shows the project run, and if you go to the CNN+SVM model, similar metrics are tracked here. We also have feature extraction time in seconds here, because this model involves a feature extraction module from the CNN, followed by the model metrics and the similar artifacts. Yeah. So that was about that model tracking part. Moving next, so as I said before, this entire pipeline is containerized, and the API is done using FastAPI service. So if I just enable the environment in this terminal, yes, and if we just copy the code for running this Docker API, so as we will see right now, it is starting the application and it has already started it. So the API service is running in this server. So if you want to give a sample input to it, we can give that using the curl command with a post request that we can see from here. So I'm giving a post request to this server URI with this sample image. So this sample image is present in the repository for testing purposes. Yeah, here it is. So if I just give it, yeah, we can see a prediction is coming, since the model is not very good right now because it's just a dummy model. So the prediction shows, and it also shows what is the drift, p-value, and etc. whether it is drifting. So it is false means it is in distribution, so it is not an out of distribution thing. Let's try with another model, another input. Yeah, for this we get a correct output. So the input is a 0 image, the prediction is 0, and the drift is false. So with this we show that the model training happens, the MLflow URI is used to track the model artifacts, and the app is also Docker containerized, which gives us an endpoint to test our sample input to the model and see. So this was the entire thing, and based on this I have also integrated a retrain workflow wherein once we, in case of any new data to the model, we can trigger the retraining pipeline. So what does the retraining pipeline do is it to support this future proofing. So that's what it is built for. In case of new data, the new data will go through the entire DBC process pipeline, and generate the required Parquet files and trigger the automated run. So if I just trigger the retrain pipeline here, so basically it will try to do a retrain on, so right now new data rows, there are no new data rows here, so it says 0, so that means no new data will be added. But in case there was new data rows which were present, the new data will be added to the existing Parquet files and it will be dumped in the same repository. Okay, right now we do not have any sample files here, so it says the model fails, but in case if you have a new data set coming here, it will start the retraining pipeline on its own. So that was about the automated retraining pipeline, and I already showed you the API service, which has 3 endpoints, which is the health, predict, and reload. So reload will load the latest production model, and the predict will predict sample output from the image, and the health will check the health status, whether all the models are loaded perfectly or not. So just giving a comparison on how the models performed. So I have detailed all the steps in this report, which I will be submitting. So yeah, these are the results so we can see the fully trained models performs very good. We see almost all predictions are correct compared to and the CNN+SVM model performs much better. These are the validation laws and training laws, followed by the confusion matrix comparison of only CNN model and CNN+SVM model, the validation accuracy, the training accuracy, and the sample curl commands for checking the inference output. So yeah, I have attached the link to the repository, so it has all the code files present in it. And if you compare the training time, so CNN local takes around, local means without using distributed training, it takes around 88.7. The accuracy is similar, but the training time is almost half for using distributed training. And CNN+SVM as well, the accuracy remains the same, but the training time is very high in local but very less in Spark because it does distributed training. So that is one comparison, KPI comparison. Yeah, so that basically shows the entire pipeline which I built from scratch. And to conclude, so I have built a full MLOps pipeline covering the training, experiment tracking, model registry, the drift detection, followed by automated training and deployment with the Dockerized FastAPI. So I believe this system can reliably handle the full machine learning lifecycle, and in the future I have plans to extend this to Kubernetes deployment maybe, and integrate with some GitHub actions for CI/CD automation and experiment with advanced drift detection methods. Currently I've used chi-square based drift detection, but it can be extended to some methods using KL divergence, etc. So to wrap things up, yeah, this is the entire project which I built, and it was a good learning experience, I would say. And thanks for that. Thanks for watching it.